So this example says that you have hot and dusty moist air composed of 15,000 kg of air, 1,000 kg of water, 10 kg of solid ammonium chloride powder at 98 degrees centigrade and 1000 millibar, and it has to be filtered through a fabric filter. The feed particle size distribution has been provided. Now this bag house has 10 cells. Now this is a simulation problem. So number of cells have been given, of which one is cleaned. There are 50 bags per cell, each bag having 1.5 meter square filtering area. Time required to clean each bag is 30 seconds. The maximum pressure drop has been given 20 millibar. The filter media resistance is also given. The outlet solid stream pressure needs to be calculated from the pressure drop. The separation efficiency is 90% at 500 nanometers. So you have to simulate the process and assess the filtration time. So let us solve this problem. For that, let us go to the properties first. Here we enter NH4Cl, and that will be solid type. Then we have air and we have water. Choose ideal method and run the simulation. Okay, so the simulation is run. So we go to simulation. So we have to specify some items over here. So first let us choose it as mix Cl PSD because we are handling solids, and the solid particles are given as it is said the feed particle size distribution is provided. So feed particle size distribution, for that we have to refer to an Excel file. So this is the Excel file that we have. It has particle size from 0 to 80. So 0 to 80 micron with 2.5 interval. So there are 32 intervals. So we have equidistance mesh type with 32 interval from 0 to 80 micron and create the mesh. So mesh is created. Now we go to the feed. Feed, we have to provide the information on the feed. It is 98 degrees centigrade and 1000 millibar pressure. So it is 98 and 1000 millibar. And the mass flow should be 15,000 kg and 1000 kg air. So air is 15,000 and water 1000. Go to solid. This is also 98 and 1000 millibar. And NH4Cl is 10 kg. So it is 10 kg. And we have to refer the particle size distribution again. So already it has been defined, only that we have to provide the weight fraction. So we directly copy it from our Excel file and then we can paste over here. Okay, so we have got the cumulative weight fraction as well. Okay, feed material has been fixed. So go to the input. Okay, now let us look at the baghouse characteristics. It says that it contains 10 cells and it is in simulation mode, right? Calculate from baghouse characteristics. So it has 10 cells, out of which one is cleaned, and then 50 bags per cell. So we have 50 bags per cell, and each bag having 1.5 meters square filtration area. So it is 1.5 meters square, and the time to clean a bag is 30 seconds. So we have to provide 30 seconds over here. Right. Diameter of bag, we keep it optional over here. So we just keep it whatever it is. Now, any more information that we have about the pressure drop. The maximum pressure drop is 20 millibar. So we go to the maximum pressure drop. It is 20. So maximum pressure drop is 20 millibar. So maximum pressure drop is 20 millibar. Okay. And then we have the information on the filter medium resistance is 10 to the power 9 meter inverse. So it is 10 to the power 9 meter inverse. And outlet solids stream pressure needs to be calculated from the pressure drop. So this needs to be calculated from the pressure drop. Okay, so apply calculated pressure drop. From there it will be calculated. And any other information that we have about the pressure drop? No, we don't have any more information. The separation efficiency will be given over here, but we have to provide any one of them, either the filter cake resistance or the dust resistance coefficient and the porosity, but these informations are not there with us. But dust resistance coefficient we can find out from our data book. So let us go to the Aspen help file once again. Yeah, so this is the resistance coefficient. Now resistance coefficient you can find over here. So now we have to see what are the size of our dust particle. Now our dust particle is from 0 to 80 micron, right? So let us check once again. We can go to the feed stream. Solid. Yes, so it is 0 to 80. So 0 to 80 micron. So our particle size is from 0 to 80 micron. So we can safely choose this one. Our data falls within 20 to 90 micron. So we will use 60,000. Okay. So that is the best figure for us. So we shall take a dust resistant coefficient of 60,000. So this is by default, it has come. Okay. Now go to the efficiency. Efficiency, the problem statement says that we have to use the separation efficiency, which is 90% at 500 nanometers. So we will directly use this one. Now our information is complete. Input information is complete, so we can run the process. Okay. So we have run the process, simulation is over. Now we have to assess the result. Now let us first go to the stream results. Let us keep it over here, stream results. So check the mass flow rate. Yeah, so our feed mass flow rate was 10 kg per hour, out of which 9.75 kg of solid we are able to filter out. And the gas flow, it is taking up 0.246 kg per hour, fine particles that it is taking along with it. If you want to see the particle size distribution, you can find it over here. So solid contains almost everything above 5 micron or so. Above 10 micron, everything is going to the solid. But finer particles, so these are all finer particles. So anything beyond this point, this is going to the solid, and finer particles are going through the gas. Okay, so this is what we get as a result. Now let us check the other results. The minimum pressure drop is 2.5 millibar and maximum pressure drop is 20 millibar. That's what we have specified. And the average pressure drop they have calculated as 11.25 millibar. Okay, so it is 20 and 2.5, average is 11.25. Here you will see an interesting thing, that total filtration area is 675 square meter. And this you have got by multiplying the surface area into the number of cells, into the number of bags per cell, and you have to subtract one clean cell from here. So it is 10 minus 1, 9 into 50 into 1.5, right? So it is 10 minus 1, so 10 minus 1 into 50 into 1.5 meters square. So this is 675 meters square. So that's what is the total filtration area. Another fact that you will get is the filtration velocity, which is 0.007285. In terms of feet per minute, it is 1.43. So maximum filtration velocity cannot go beyond 20 to 40 feet per minute. So it is well within the limit. And this is another interesting thing, is the filtration time. You can see the filtration time is very, very high. It is 270 hours. Okay. So 270 hours filtration time is very high. Now the reason for this high filtration time is we are allowing the maximum pressure drop of 20 millibar. Now that much of allowance is not required. Because it is having a higher allowance of pressure drop, it is allowing more and more dust particle to settle on the surface of the filter, and the cake thickness is getting larger and larger. And as the cake thickness becomes large, the resistance due to the cake will also be large, and as a result, the filtration velocity will also be lower. You can see the filtration velocity is 1.43. That means it has penetrated that thick cake in order to go to the other side and get cleaned. So it is taking much more time because you have allowed more amount of pressure drop, which is not required. So our second problem is about that, which says that you reduce the filtration time to 2 hours and take pressure drop of filter media to be 3 millibar and simulate the process. So now we will fix the filtration time. We will say that no, we are not going to wait for 270 hours. Rather, we want to finish our filtration with 2 hours, and our filter media pressure drop is 3 millibar. Do the simulation. Now, for that matter, we will check the result that we are having right now with the result that we will see later. Okay, so let us change the values. In the new case, our filtration time is 2 hours, and pressure drop of the filter media, we will change it to 3 millibar. So we will change it to 3 millibar. And all other things we will keep it same. Okay, let us not disturb others. Only these two things we will change and rerun the simulation. Okay. Now we have not changed the efficiency, so we cannot expect any change in the stream result. It will be same as 9.75. So the efficiency will be 97.53% or 0.9753. So that will be the efficiency. It is the same. Okay. But what are the other things? You can see the minimum pressure drop. It is 3 millibar. Maximum pressure drop, it has calculated. Now we have not fixed. But as you have given the minimum pressure drop, that means the pressure drop due to the filter media, you have specified as 3 millibar. So it has calculated the maximum pressure drop based on the time that it takes for filtration, so that you have allowed only up to 2 hours time for filtration, and you have not allowed the thickness of the filter cake to go beyond a certain height. And as a result, the maximum pressure drop, that means the pressure drop due to the filter medium and the pressure drop due to the filter cake, combinedly the pressure drop, that is the maximum pressure drop, is now 3.1295 millibar only. And here you can see the filtration velocity is same as 1.43. Okay, so that's how the simulation occurs. Now go to the next problem. Next problem says that assume average pressure drop is 10 millibar. Now it is neither the minimum nor the maximum. We are rather specifying the average pressure drop. And outlet solids stream pressure is also we are fixing at 0.9 atmosphere. Filtration velocity is also we are fixing, where its minimum and maximum velocities are also we are fixing. Now design the fabric filter where the filtration area may be calculated from the velocity. So now it's a design problem. So let us look for the design mode. So for that, let us first go to the design mode. Okay, design mode. You have to provide the average pressure drop. So press constant. Average pressure drop is 10 millibar. So this is 10 millibar. And filtration velocity you have to provide 0.01. Minimum is 0.001, maximum 0.03. This is 0.03. This is 0.001. And this is 0.01. Okay. So these three things we have provided. And calculate it from the velocity. So we have to calculate it from the velocity. So we have provided the velocity information. Right. Now you run the process. Okay. Now go to the result. So the average pressure drop, overall efficiency will not change because we are not changing the separation efficiency. Rather, we are not doing anything for last 3-4 simulation. We are not doing anything over here. So the efficiency will be same. So efficiency is same. The total filtered area is 491. Earlier, we were getting 675, but design says that we do not have to use 675 meters square. The kind of efficiency that you are getting, that you can anyway get with 491 meters square of filter area. So this is about the design problem. Now, next problem is redesign the process by calculating the filtering area from estimated velocity and baghouse characteristics. Take the filtration velocity function that we have learned some time back, where filtration velocity is in meters per second and pressure drop is in millibar. So we have to redesign based on this information. So first, let us change it to calculate from estimated velocity and baghouse characteristics. And then we have to take this one, filtration velocity function. And here you have to use the velocity unit as meter per second and pressure drop as millibar. So it is meter per second, pressure is in millibar. And then delta P is equal to 3 plus 4.7 V plus 5 V square. So it is 3, 4.7 and 5. Okay. Well, pressure unit is millibar. Okay. Now everything is set. Now we can rerun the design problem. So we have rerun it. Now let us go to the result. As expected, there is no change in the overall collection efficiency because we have not changed anything with the efficiency. But the total filtered area has increased to 1950 because here they are saying that a baghouse should contain 27 number of cells. Okay. Obviously, this design is not very efficient design. Now we come to the last problem. Here it says that repeat the design with separation efficiency function of this. Now we have changed the efficiency function. Now let us go to the efficiency function over here, change it to define functions with coefficient. And we have to provide the value of A, B, and C. So A is 1.06, B is 10,900, and C is 0.2. So we have to write 1.06, then 10,900, and this is 0.2. Okay. Okay. Now we will expect some change over here. The collection efficiency, there will be some change. Let us see. We will run the simulation. Yes. Now we are getting 99.7% efficiency. Now look at the stream result. We have got 9.97 kg of solid that is being recovered in the solid outlet, whereas only 0.02 kg is going through the cache. No need to see the PSD, but if you want to see, you can just check the particle size distribution of feed and the particle size distribution of the solid. They are almost same. That means the entire solid particle, almost entire solid particle has moved from feed to the solid. And whatever is there in the gas phase, they are mostly in the finer zone, not in the higher zone. With that, we come to the end of this lecture. I hope you have enjoyed it, and we will come back with yet another interesting lecture very soon. Thank you.